All right, so let's look at the solutions to the rest of those test practice problems. Problem 4 says a proton is accelerated in a uniform electric field through a potential difference of 5,000 volts. What is the kinetic energy of the proton in electron volts and in joules? I should have made it clear that this proton is beginning from rest. I wanted you to use the work energy theorem. We know that the amount of work is going to be equal to the change in kinetic energy. But when we have something accelerating in a uniform electric field, the work is equal to the charge times the potential difference. Remember, you might have seen it written as VA minus VB. This is a proton. If the electric field is doing work on this proton, it is going to naturally move from a high potential to a low potential. So in this case, the charge is one electron or one elementary charge times 5,000 volts. We can think that in terms of it was 5,000 to 0. It's a 5,000 volt potential difference. This simply equals 5,000 electron volts. So if we want to just get it in terms of electron volts, proton has a charge of 1 electron, 5,000 volt potential difference. It's very straightforward. We can do the same thing and say this time we're going to do it in joules, so we'll have to use the charge in coulombs. 1.60 times 10 to the negative 19 coulombs. And again, a potential difference of 5,000 volts. If I put that in my calculator, I get that the kinetic energy or the work done is 8.0 times 10 to the negative 16 joules. In either case, that will be the kinetic energy. So again, so I found work, but that's that work energy. The kinetic energy is equal to the work. It's after leaving the uniform electric field, the proton is headed directly towards a silver nucleus. Silver has an atomic number of 47. That means its nucleus has 47 protons in it. If the proton is initially 2 meters from the silver nucleus, how close will it get to it? The silver nucleus is held fixed throughout this process, so it can't move. So we've got a silver nucleus over here. It has a charge of positive 47 E. And then we have this single proton here that's moving towards it. I didn't give you a hint, but the hint, if I gave you one, would have been use conservation of energy. We know the distance that this starts out is 2 meters. We can easily calculate the charge on the proton. We know it's 1.60 times 10 to the negative 19 coulombs. The charge on the silver nucleus, 47E, is 7.52 times 10 to the negative 18 coulombs. Okay. Conservation of energy just looks like this. We have an initial potential and an initial kinetic, and it will equal the final potential plus the final kinetic. Okay. In this particular problem, initially the proton has both potential and kinetic energy. It has potential energy. Our potential energy formula is K, Q, Q prime, or Q1, Q2. We have two different charges over the distance. That's our formula for potential. Our kinetic, we know. Initially, our kinetic energy is 8.0 times 10 to the negative 16 joules. When it stops, so it's going to travel, 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 but remember, it's being repulsed. It's going to stop when its kinetic energy is 0. So at the end, we're going to have our final potential energy, which will be K, I could put this as initial distance, Ri, K, Q, Q prime, final distance. And the kinetic energy will be 0. When it stops, the kinetic energy is 0. So let's look at how much potential energy it even had to begin with. Even though 2 meters may not sound that close, or that's really, or that far apart, that's really far apart. The potential energy for these small particles is probably going to be almost 0, even though it's not infinity. It won't be 0 until R is infinity. So we've got 8.99 times 10 to the 9th. We've got 1.60 times 10 to the negative 19. 7.52 times 10 to the negative 18. And the distance there was 2 meters. Plus this 8.0 times 10 to the negative 16. And we know when we get finished, that's going to be this final potential, this K, Q, Q prime, R final. Well, when we calculate this initial potential energy, it comes out really small. It comes out to be 5.4 times 10 to the negative 27. The initial kinetic, remember, was 8.0 times 10 to the negative 16. When you add those two together on your calculator, this number is so small compared to this number that when it adds them together, you still just get this number. Think about that. These would have a bunch more zeros when you're writing out that tiny little decimal before you even got to the 5.4. So really, this amount of kinetic energy just has to equal K, 8.99, 8.99 times 10 to the 9th, Q1, 1.60 times 10 to the negative 19, Q2, 7.52 times 10 to the negative 18 over R final. And R final is what we're looking for. I wish I'd left a little bit more room. Let's see if I can, I don't think it'll let me write out here in the empty space. No. See if there's a little room at the top of the next page. There it is. So if I want to solve for R final, I get that R final is all of that stuff on top divided by 8.0 times 10 to the negative 16. And I get that R final is 1.35 times 10 to the negative 11 meters. So it will get really close to that silver nucleus, but it won't actually touch it. Remember, they repulse each other. It will eventually turn all of that kinetic energy, and all of that kinetic energy is really just this 8.0 times 10 to the negative 16. This little bit of potential energy was so small, it really almost had no effect on our answer. Strictly conservation of energy. It had some potential, not very much. It had kinetic, that was 8 times 10 to the negative 16 joules. Once it stops, its kinetic will be 0. It's going to keep getting closer and closer, but remember, it's going to be slowing down because they're repulsing until eventually it will stop. At that point, this is rather like throwing a baseball straight up. It will slow down all the way up till eventually it will stop, and then it'll actually turn around and move back the opposite direction because of the repulsive force. Our next problem deals with, it says 3-point charges are located at the corners of a square that is 0.40 meters per side. The charges at point B and C are positive 5 microcoulombs. So if we wanted to draw this right here, there'd be a positive 5 microcoulombs. Right here, there'd be positive 5 microcoulombs. But down here at point D, there is a negative 3.6 microcoulombs. It says, what is the electric potential at A? So we're looking right here, and they're saying, what's the voltage? What's the potential at that point? Now, the potential due to B and C will be positive, but the potential due to point D is actually negative. However, looking at the size of these charges, I feel like the total potential should come out to be a positive value. It's like adding hills and valleys. I think my hills are going to be bigger than my valley. Potential's nice. It's not a vector quantity. The potential due to a point charge is just given by the formula V equals KQ over R. If you have multiple charges, then just add them up. In this case, we have 3 charges. We do need to find the distances. It said it was a square. So this side is 0.40 meters. But this distance is the diagonal of the square. And we have to do the Pythagorean theorem, or maybe you remember that it's the side times root 2. But if you do the math, you're going to see that that distance comes out to be about 0.56. Where's my pen? There it is. I have 0.5657, I believe. Like I said, that's just the Pythagorean theorem. I'm going to double check it real quickly. 0.4 squared plus 0.4 squared. Take the square root, and you get 0.5657 meters. So we have that distance. We need to just fill in our charges. I'm going to go ahead and factor out this K, just because I don't need to. It's 8.99 times 10 to the 9th times Q1, I'm going to say it's 5.0 times 10 to the negative 9 over 0.40, that's the distance between point B and point A, we're trying to find it right here, plus Q2 is also 5.0 times 10 to the negative 19. I'm sorry, negative 9, not 19, just 9. But it's a little farther away, 0.5657. And then finally, at point D, we actually have a negative charge, so 3.6 times 10 to the negative. Let me fix this. Okay. Micro is 6, not 9, so this should have been microcoulombs 10 to the negative 6, 10 to the negative 6, 10 to the negative 6. That distance is also 0.40. Now it's just a calculator problem. And it comes out to be, when you put it in the calculator, you get 110,924. It's a pretty big number. We only have 2 significant digits in this problem, so we're just going to keep those 2. So I would write that in scientific notation as 1.1 times 10 to the 5th volts. So lots of potential at that particular location, but a very straightforward problem. Potentials are so much easier to calculate than electric fields or forces because it's not a vector. The last 3 problems are all about capacitors. Problem 6 says The plates of a parallel plate capacitor are 3.28 millimeters apart, and each has an area of 12.2 centimeters squared. The plates are in a vacuum, and each plate has a charge of 43.5 nanocoulombs. What's the capacitance? Well, we have all the dimensions. So capacitance, of course, is going to be this epsilon naught, that's vacuum permeability, times the area over the plate separation. So our constant here, that's 8.85 times 10 to the negative 12. Now the area needs to be in meters squared, but that's an easy fix. I have 12.2 centimeters squared. I know that 100, oops, doing this upside down, watch me. I know that 1 meter is 100 centimeters. I need to square that because I don't want centimeters or meters. I want square meters. And the distance, 3.28 millimeters, is 0.00328. That's also in meters. Now it's just a calculator punch. I put all that in my calculator, and it comes out to be 3.29 times 10 to the negative 12 farads. I feel good about that answer because I know that capacitance is normally either microfarads, nanofarads, or picofarads. It's a small quantity. I could write that as pico. Negative 12 is pico. That's 3.29 picofarads. It's fine to write it in scientific notation. It's fine to use the prefix, whichever one you like. What is the potential difference between the plates? So what's the voltage? Well, we know capacitance is the ratio of charge to potential. So V is equal to Q over C. The charge is 43.5 nanocoulombs, so 43.5 times 10 to the negative 9. That's coulombs. Capacitance is 3.29 times 10 to the negative 12 farads. I put that in my calculator, and it comes out to be 13,200 volts. I had 3 sig figs, so I wanted to round that to exactly 3 significant digits. What's the electric field between the plates? That one's usually pretty easy if you know the potential and you remember that electric field can also be expressed as volts per meter. So for uniform electric field can be found just using volts divided by the plate separation. I have 13,000. If I use my unrounded number, it was 13,215 volts. I have a plate separation of 0.00328. That came out to be 4.03 times 10 to the 6th volts per meter. If we only had 2, that might be written as 4.0 megavolts. It's a big potential. I mean, a big electric field. It was pretty straightforward there. Problem 7 addresses the idea of 2 capacitors that are connected in series with a 12-volt battery. So I have a 12-volt battery, and then I've got 2 capacitors. There's one capacitor, maybe here's the other capacitor, and they're connected across this 12-volt potential difference that goes from here to here. So 5 microfarads, 10 microfarads. You don't really need a picture, but why not? Equivalent capacitance in series is 1 over equivalent capacitance equals 1 over the first. I'm going to leave it in microfarads because I'll just get my answer in microfarads. Plus 1 over 10. If we want to show off our use of fractions, the common denominator here would be 10. That would be 2/10 plus 1/10 is 3/10. But I need the reciprocal of that. When I do the reciprocal, I get that the equivalent capacitance is 3 point, and the 3's repeat, you get to 3 sig figs, 3.33 microfarads. And then it says, what is the charge on the 5 microfarad capacitor? Well, what you want to remember is that when you are in series, all plates have the same charge. The simplest way to find it is to use this equivalent capacitance and say, if I had a 12 volt potential difference and a 3.33 microfarad capacitor, what would Q be? Well, C equals Q over V. So our formula is going to be Q equals CV. If I use my unrounded formula, which is going to be 10/3 microfarad times my voltage, which is 12 volts, I get exactly 40 microcoulombs. You can do this with a calculator. I just thought, 3.33 is exactly 10/3 here. We flip this over, times 12, that's going to be 120 divided by 3. It comes out to be exactly 40 microcoulombs, although I do have 3 significant digits, so I really should write that as 40.0 microcoulombs. Remember that micro is a 10 to the negative 6, but we can treat it just like that, carry it along. Finally, we're going to do one. Same, it says the 2 capacitors from problem 7 are now, oops, that's a typo. Please read that as now. Now connected in parallel, not connected in parallel. Are now connected in parallel with the 12 volt battery. What is the equivalent capacitance? All right. Here's my 12 volt battery. I have one capacitor. Notice there's we'll connect up there. And then I have another capacitor. One of them's 5, one of them is 10. But the nice thing, equivalent capacitance in parallel is just the sum. 5.00 microfarads plus 10 microfarads is 15 microfarads. What is the charge on the 10 microfarad capacitor? Well, the important thing to know about the 10 microfarad capacitor, well, that's supposed to say 5, it didn't copy very good, is that the potential is 12 volts. When you're in parallel, they all have the same voltage or the same potential. So if I say C is Q over V and I want Q is C times V. If I'm doing it for the 10 microfarad capacitor, the charge, I'll call that one capacitor 2. It's going to be 10.0 microfarads times 12 volts. 10 times 12 is 120. Still have that microcoulombs. Notice it holds a whole lot more charge than they did when they were wired in series. In series, that capacitor only had 40 microcoulombs of charge, but in parallel, it can have 120 microcoulombs of charge. You're always going to store more charge and therefore store more energy if your capacitors are in parallel. Okay, I hope those problems help clarify some things, and I hope they help you be successful on the test.